What is a matrix? A matrix is a rectangular array of numbers arranged in a format of rows and columns, as we learnt from Math 141. They are a useful method of displaying, interpreting and manipulating a set of numbers for various applications. Some real-life applications of matrices in engineering are as follows: seismic surveying and geotechnical engineering, electrical circuits and electrical engineering, computer programming, robotics and mechatronics engineering, and balancing chemical equations in chemical engineering.
In this first example, we are utilizing an electrical engineering concept, and the objective of this is to find the current of the two-port network and to represent it in a matrix form. So the first step is to label the nodes. So we have node 1 and node 2, so we labeled it I1, V1, I2 and V2. So using the augmented system for the matrices, we obtain an equation for I1 and equation for I2. So the next step is using Ohm's law and nodal analysis and Kirchhoff's current law at node 1. We are going to solve to find two different values. So minus I1 plus V1 divided by 0.5 plus V1 minus V2 divided by 0.5 equals 0. This way, just solving through with simple algebra and mathematics, we're going to obtain two values which are 4 and negative 2. Now the next step is exactly the same thing, but this time at node 2. So we're going to be using KCL, Ohm's law, nodal analysis, exactly the same process. And this time we're going to obtain this equation with these two new values, minus 2 and 4. Now that we have four different values, 2 from KCL at V1 and 2 from KCL at V2, we are going to represent the solution as a matrix. And we're going to do so by using that formula that we had at the beginning, that same system, and all we have to do is just sub in the values. So in this case, we're going to have 4, minus 2, and 4.
Alright, so this example utilises matrices to help balance chemical equations. As we can see here, we have quite a simple chemical equation, and we label each of the coefficients with an x. So we have x1, x2, x3, and x4. Then down here, we split it up into each element. So in the first compound here, we have 6 carbon atoms. So we have 6x1. No carbon in the second one, so it's 0. 1 carbon in the third one, so it's 1x3, and no carbon in the fourth one. We repeat that for both oxygen and hydrogen until we have 3 simultaneous equations. We take all the elements onto the left-hand side, so they're equated to 0, so we can have and chuck it in an augmented matrix, as we can see here. So we have all the x's and all the elements. Then we use row reduction. So we have R3 subtract R1, and with this matrix, the next one we rearrange things by dividing R1 through by x, R2 by 2, and R3 by x to get this matrix. Then we move on to this one where we add R3 to R1 to simplify it even further, and finally we multiply R3 by 6 so that we have the matrix we want with the desired elements. We then move that on and find our value, equate to our values of x1, x2 and x3, all in terms of x4. Then we move on and we say x4, we let x4 equal to 6. That allows us to obtain x1, x2 and x3 in all the lowest form of whole numbers, as we can't have any fractions or anything like this because it's a chemical equation, until finally we get our final balanced chemical equation.
From these two examples, we're able to observe the applications of matrices to various disciplines of engineering. Thanks for watching.